But I don't think in Algebra 2 you ever talk about this, but it is true. Whatever your degree is, your graph will have at most one less than that turning point. And that's what it means. A polynomial function of degree n has at most n minus 1 turning points. The math term there is local extreme points. And at most n zeros. Maybe you remember from Algebra 2 that if it's degree 2, it should have 2 zeros, but sometimes we kind of talk about imaginary zeros. But when you start graphing those higher degree polynomials with all the terms in them, sometimes it's nice to remember this, that if you have an x squared function, that's going to have at most one turning point. And that's true, right? What's the graph of a quadratic look like? How many turning points does it have?
One.
Only one. That's easy. If you had a fifth degree polynomial, like x to the fifth, it could have at most 4 turning points. It could have less, but it could have at most 4 turning points. And so when you're graphing these, sometimes it's nice to know that. Sometimes they might ask you what's the highest degree this could be if they gave you a graph, and it would be 1 less than the number of turning points. And then we're just going to start here with a nice cubic graph, just because it's been a while since we graphed cubic graphs. And I think there's one on your homework like this today. Again, transformations help with every type of graph, whether you're talking about a quadratic, a cubic, an exponential, a log graph, even trig graphs that we haven't even learned yet. The transformation rules are the same, so that's why it's so nice to know what it means when there's a number multiplied out front, or when there's a negative out front, or when there's a number added or subtracted on the inside, or added and subtracted on the outside, because it's supposed to make graphing easier, or at least let you verify that your graph is correct. And so it says, describe how to transfer x cubed into 2 times x minus 3 cubed, then sketch the graph and give the y-intercept. Just to reiterate the directions in the homework. Sometimes I say when it says check graphically, you don't have to do it, because check graphically means they want you to just verify your answer using a graphing calculator. But if it says sketch the graph, that means they want you to actually draw the graph out, and I want you to actually draw the graph out. And so there are some in your homework today that say sketch the graph. Like the very first one is just like this. I do want you to sketch the graph. Do you remember what x cubed looks like? It's one of those 10 functions I told you you should know the rest of your life. Aaron Cole calls this an S graph. I don't know why we call it an S graph, because it's really not an S. But it's an odd function. It's my favorite odd function. But it just kind of goes like this, kind of little curve there in the middle. Which means if you know what this does to the graph, and you know it's this shape, you might not have to pick a million points. What does a number multiplied in front of the function do? Yeah, it stretches it. Actually, we could even say that it's stretched by a factor of 2. Not by 2 units, but like twice the amount stretched out. And what does a number subtracted inside the function do to that graph? Left or right, and because it's minus, it's actually right 3 units. If it's outside the function, it's up or down. All right? It does ask you to describe it, so you kind of need to know it. If it just asks you to sketch it, it's not required that you have to say that stuff, but it's nice to help you when you're graphing it. The problem with cubic graphs is they get really big and really small very quickly. Which means I don't know how many points we're actually going to pick, but it helps us at least know how stretched out to make our graph. Starts at 0, so even if I stretch it by a factor of 2, that's not going to start at 0 because I moved it over, right? So when I teach Algebra 2, I always tell kids, if you're not sure what to do, pick what's going to make whatever that function is go to 0. So when I see x minus 3, I know I'm going to pick 3 first, because I know 3 minus 3 gives me 0, times 2 gives me 0. If it's a square root, I'm going to pick what makes it go to 0. If it's a quadratic, I'm going to pick what makes it go to 0. If I'm not sure what the graph looks like, I'm always going to start with what makes it go to 0. And why does that work? Because normally it starts at 0, and I just moved it over 3 units. And if you can find that first point, On an absolute value, it's like the V. On this, it's going to be like that little kind of turning point, not really. If you just pick one above it and one below it, or one to the left and one to the right, it should work out really nice. Like if I pick 2, if I plug 2 in there, I'm going to get negative 1 to the third, which is negative 1 times 2, which is negative 2. And normally on this graph, if you go over 1, you get 1. If you go back 1, you get negative 1. I just stretched it by a factor of 2, so when I go back 1, I now get 2, which means what should happen when I plug 4 in there? And I said negative 2. I said 2, but I meant negative 2. If I go this way, I should get positive 2 because it stretched out. Normally when you plug 2 in here, 2 to the third is 8, which means if I plug the next number in here, it's going to be stretched by a factor of 2, which means it's going to be like 16 units one way or the other, which means I'm not really going to make that on my graph, but when you graph it, you need to make sure you show that it's really stretched out, which means if you picked, let's just plug 5 in here for a minute. This is going to be 2. If I plugged 5 in here, I'm going to get 2 to the third, which is 8. 8 times 2, which is 16. Which means this would be way up here. So how do I show that? Pretty much go straight up and straight down, because it's not really going straight up, but it's going up so quickly that that's how I'm going to show that on the graph. Without having to make that graph. Again, transformations help you, but you can do it without transformations as well. So graphing never goes away. Okay. What else? Let's talk about the end behavior, the leading coefficient test. I've kind of already talked about this year, but if you don't remember the whole arrows, which way the arrows go, this is my little chart of how to write this out. And so, again, I like to write a polynomial like this, where this is your leading coefficient, n is your degree, and I just kind of wrote it all the way out. But if you just want to write leading coefficient test, and just write with degree n, and you don't want to write that part, you don't have to. In Algebra 1 and Algebra 2, and even in this class, we always ask, is it a polynomial? What is the degree? What is the leading coefficient? And that's because we can tell a lot about a graph based on the degree and the leading coefficient. And so, Mr. Dorsett, who used to teach in this room a long, long time ago, he had this little chart that he always made, and I thought it worked out really well. So I like to make the same chart, where if n is odd, we can talk about if the leading coefficient is positive or the leading coefficient is negative. And if n is even, we can talk about if the leading coefficient is positive or negative. White beard? No. No. Mr. Who was in the room before that? There was, I don't know. There were other teachers before him, but I don't know. He taught me for like 7 or 8 years, and then he quit to go sell math software. Now he sells Mathematica software. I don't know. When n is odd, your arrows will always go in opposite directions. How do you know whether it's positive or negative? So I'm going to kind of draw the picture, and then I'm going to write it out. If it asks you to describe the end behavior, you have to actually write it out. If it doesn't ask, you can draw the picture. But when n is odd, to me it makes sense that the positive side goes up and the negative side goes down. Lots of stuff can happen in the middle, but if you have an odd degree with a positive leading coefficient, then the right side goes up, the left side goes down. So how do we write this? As we do it, you're probably going to remember. We can say as x goes to infinity, so as x is getting bigger, the function or the y values are also getting bigger. So we say as x goes to infinity, f of x goes to infinity. And as x goes to negative infinity, that would be as x gets smaller to the left of your graph, what happens to my function? It also gets smaller, so it goes to negative infinity. Remember writing that out last year? The nice thing is, this part is always the same when you're talking about end behavior. What happens as x gets bigger? What happens as x gets smaller? And you just tell me what's happening with the y values. This is all that changes, which means you really got a 50-50 guess every time, right? It's either infinity or negative infinity. Hopefully you're not guessing, but If the leading coefficient is negative, they switch. So if the leading coefficient is negative, now the negative side goes up and the positive side goes down. I like to know this when I'm graphing, even if it doesn't ask, because it helps me not have to pick a ton of points if I know what's going to happen at the end. But I'm going to say, as x goes to infinity, this is where you can practice your infinity signs. Don't make two circles next to each other anymore. Practice. What? Oh, what, do you make them the correct way now? Olivia Arnold refuses to make them this way. Why? She just says she's not doing it. She's just making two circles. No, I just cry a little every time I break it.
You like a little infinity scan, you just scan.
It's just practice. It's not that hard.
Why?
When it is even, think about quadratics. They either both point up or they both point down. All about the leading coefficient. I feel like we've been doing quadratics for so long that you don't even really have to think about this, because if it's a positive x squared, we know they both point up. Like this. If it's a negative x squared, they both point down. But that works with any even degree polynomial. So we say as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x also goes to infinity. Again, this is the only part I'm changing every time. And this one, they're just both down. As x goes to infinity, f of x goes to negative infinity, and as x goes to negative infinity, f of x goes to negative infinity. There are some questions on your homework today that say describe the end behavior, and there's a question on your test that says describe the end behavior. And just drawing the arrows is not describing it. Yes, it's nice to have the picture, but you have to write it out in these lovely math terms. Okay? Questions about that? Ethan? Come on. Terrible answer, but yes. I always like to say this is disco, but I don't really know if it's disco. This goes more like this, right?
I think this is actually Excel.
It's the math odd coefficient.
Do it at pi day.
I'll do it at pi day just for you. Can I go? Everybody okay with this? Oh my gosh. How many more things can we write? Right? This is another thing that we don't really talk about in Algebra 2, but I don't know why we don't, because it's kind of a really nice thing when you're graphing. If you have a degree that's even or odd, you have a 0 with an even or odd power. So it says if you have x to the n, where n is an integer, and n is greater than 0, because if it was negative, that would throw things off. If it was a fraction, that would be weird. If you have an even degree, wherever your 0 is, wherever your x-intercept is, it's just going to touch the x-axis. It's not going to cross the x-axis. My best example of that is thinking about x squared. You can see I didn't even erase it all last time. If you have y equals x squared, its x-intercept is at 0, but it doesn't actually cross the x-axis. It just touches it there and then it goes back up. As opposed to if it's an odd 0. If you have an odd 0, then at the x-axis, it's going to actually cross it. And think about x cubed. We just graphed x cubed. Right? It has a 0 also at 0, but this side goes up and this side goes down. And that's true for all even and odd zeros. So if you have an even one, it's just going to touch. If you have an odd one, it's just going to cross at whatever that 0 happens to be. Which again tells us a lot of things. Remember last year in Algebra 2 when you graphed these and you just had to pick like 10 points? Using all this stuff together makes it where we only have to pick maybe 3 points, maybe 4, to get a really good graph of these. The good thing today is already in factored form for you, and so it says find all the zeros and describe the end behavior, and we're actually going to go ahead and say if each zero crosses or touches the x-axis based on the power out here. But it's already factored for you, which means if we want to find the zeros, we just set that equal to 0, and we just set each factor equal to 0, right? So you're not supposed to have to do a lot of work today. Super great. If this is x minus 1, do you agree that the 0 has to be at 1?
Yes.
And this has to be at -2, and this has to be at -3. Oh, well, they're also easy, right? We could also say, what is the power of each of these zeros? But there's nothing on there, which means it's the power of 1, right? Is 1 even or odd? Odd, which means I can tell you that all 3 of these zeros are going to cross the x-axis. So sometimes the directions will say, tell whether each 0 touches or crosses. This doesn't say, but I'm going to go ahead and say that all of these cross the x-axis. Oh, and describe the end behavior. You do have to think about these that it's not multiplied out. What would the highest degree of this function be if I multiplied all that out? X times x times x would be x to the third, which means it's odd, and the leading coefficient is positive, right, which is 1. So the end behavior, you have to think about what the highest degree would be, and then you have to tell me what the end behavior is. And every time it asks you to describe the end behavior, this is what you should write. As x approaches infinity, f of x approaches something. As x approaches negative infinity, f of x approaches something. And if it's odd and positive, what's it going to be? Infinity, negative, infinity. Positive stays positive, negative stays negative. Right? That's not bad homework. So we're going to do on number 3 first. Zeros or end behavior? Neither. Zeros. It's too late now.
Erase it. Can't do that.
If I set this equal to 0, right? It's okay, it's going to be a fraction. I'm going to subtract 1 and divide by 2. Again, if it's to a power of 1, it's always going to cross, so I'm going to go ahead and just say it crosses the x-axis, just kind of getting a habit of that. What about this one? I should have made that an even number, but I didn't. X minus 4 to the third power. The 0 here is still just going to be 4, because you could take the cube root of 0 is still 0. But that degree is what determines whether it crosses or touches. Since it's still odd, even if it's a third degree, we're going to say it still crosses. If that would have been a squared or a fourth or a sixth power, an even number, we would have said it only touches there instead of crosses.
So if it's odd, it's going to cross, and if it's even, it's going to touch.
Yes.
And if it's, I guess it's
Right. What would be the degree of this if we worked it all out? The idea is I don't want you to have to multiply this all out, right? We're just looking for the highest one. So if I took x minus 4 to the third, what would be the first term? So it would be x times x times x. So then if I took x to the third times 2x, it would be 2x to the fourth. Right? You could work it all out, but you're just looking for the biggest one. So you're trying to just multiply out the first term or the biggest term in your problem there. Which means it's even and a positive again. So as x goes to infinity, f of x goes to infinity, and as x goes to negative infinity, f of x goes to infinity. If you struggle writing this out, draw the picture to help you, to remind you which way it's going, and then you can fill in the blanks there. Questions?
so you just multiply the like biggest number.
The biggest x. Does that make sense?
Yeah, that's from 2 because all of the zeros.
Yes.
Okay, I'm sorry. Could you explain where you got the 1
this out, like I could write this out as x minus 4 times x minus 4 times x minus 4, right? And it would be a lot of work to work it out because you'd have to FOIL it out and then multiply again. I know I'm just looking for the degree, so I'm just going to take the biggest x from each one. So I just said x times x times x. I know that's going to give me x to the third. And then take that times the biggest x in the other one. So 2x times x to the third is where I got that. And it just saves you some time because you don't really care about all the rest of it. You just care about the biggest ones. All right, and there's some in your homework today, so we'll kind of see what questions we have as we do that tonight. Oh, I don't think we're really going to do this again. Oh my gosh, what about this? What did I just skip? 4 and 5, so this should be 4 now, right? I think you said indicators. You did indicators, so. Again, we're not going to talk about the crazy way to solve polynomials yet, which means when it says find the zeros of the function algebraically, you should be able to use techniques that we've already learned this year. And really, the only technique that we've learned this year to solve these, factor. And maybe at some point you might have to do the quadratic formula after you factor something out. But we haven't talked about other ways to do this yet today. So when it says algebraically, factor is kind of what we're looking at. And I think on this one, I can factor out a 5x. And I can kind of make it just look like the ones that we just did, where it's set equal to 0. What does that give me? X squared minus x minus 2. Is that factorable to the lower? X minus 2, x plus 1. And so this looks like the one that we just did, only it wasn't factored out for us, but now it is. So now if I'm finding the zeros, now I just set each one equal to 0. And again, we could say if they touch across, that's really not necessary. That's just 0, that's just 2, that's just 3. So again, factoring just really doesn't ever go away from us. I don't know how many we have left. Oh my gosh, we don't have any left. Good thing. 3, 6, and then 18 through 36 multiples of 3. I should just throw 24 out, but I'm not because it's just a weird one in there. It's not factored. So on 24, maybe just write on your paper, 24 just do in behavior. Probably someone will ask about 24 tomorrow and say, I don't know how to do it, and then I'll remind you that you only have to do in behavior. So, but for the rest of them, do what the directions say.